And thank you also, organizers. I'm very happy to be here.
Oh, thank you very much. It's a bit small, but
So today I want to talk about some families of quasicrystals, like kind of like some classification into different families of quasicrystals depending on some behavior. So first I want to tell you where the name comes from, the quasicrystals. So first, what we need to know is what's a crystal. So a crystal is a material that has a periodic atomic structure. And mathematically, the way it's a subset on R to the D, and we usually ask it to be uniformly discrete and relatively dense. So uniformly discrete is these are like points. Uniformly discrete means that there's no 2 points that are very that there's a minimum distance and kind of like a maximum. That but there's also like the discrete version. Would be something here. So we're assuming each point here is an atom. And one of the properties that's experiment the X-ray diffraction spectrum. So this is an experiment where they take a material and they put an X-ray, and then you see like the shadow of the light, and what they see with the crystals is they see only points. So it's kind of like you see points and it has. So I think Michael is going to do an experiment later in the week, so you can see this. So the physicists thought that the only possible way to get this pure point diffraction spectrum was with the periodics, with like crystals, but then they discovered later some materials that have the pure point diffraction spectrum, but were not periodic. So there exists, and they call this quasicrystals. So it has pure point diffraction spectrum, but not periodic. So given these are kind of Delaunay, is kind of the mathematical name is like Delaunay set. So given a Delaunay set, you can construct a dynamical system, which is kind of like XD. This is the. So the whole, you can think this in two ways. You can think, you take kind of like a point here, and then you take the shifts, all the shifts, and then you take the closure. But also another way to interpret the whole that is less dynamical is kind of like the space of points that have the same language as what you see here. So for the physicists, they like more this rather than the dynamical version, they like the version where you see like it's all the points that have the same language as D. And then you have some, so you have some, so maybe RD or maybe CD, so action by translation. And with some hypotheses, which are also natural in the physical, which it's kind of like uniform frequency. Which is it's kind of natural in the, because it's kind of like you want these materials to have like regularity properties. So these systems are uniquely ergodic. And there's a nice theorem, Michael and Daniel Lenz. For a uniquely ergodic XD, pure point diffraction spectrum if and only if pure point dynamical spectrum. Okay, so I'll tell you what's the dynamical spectrum. So this is kind of like the spectrum that you see in like Halmos, von Neumann. So it's also very nice that kind of like this pure point or discrete, like they usually meant completely different things, but they're very connected. And I think this and others, I mean, I think this has been done in different generalities. But I think this is kind of the first. Okay, so what's this? So what are the eigenfunctions given a measure preserving action? We say f is an eigenfunction if there exists some element, I don't know, W in the dual. So right now I'm writing G is kind of like either RD or set to the D, such that F composed with the shift by element G is okay. So this is in the dual. So it's a function that goes to the and these are a complex value. So the way I see it is this: F is kind of like an observable. So it's telling you, it's giving you some information about points in the system. And then this is kind of like this is what's sometimes called the Koopman operator. So this is kind of like the dynamics on the observables. So on the functions. And this is a number in the unit circle. So what it's telling you is that the dynamics on the function looks kind of like, so this is a number in the unit circle, so it looks like a rotation. And actually it is connected to, so pure point spectrum means eigenfunctions generate L2. And this is kind of old, but it can be adapted. So this is almost von Neumann. So for ergodic systems, pure point spectrum, if and only if isomorphism to a group rotation. Okay, so from the point of view of ergodic theory, if you have pure point spectrum, I mean, you have everything. You have isomorphism theorem by looking at the spectrum. You have a lot. And then from a topological dynamics point of view, it's telling you that there's a nice topological representation for every system with a pure point spectrum. But that doesn't mean all of the models are that well behaved. Actually, there's results by a letter, or like you can find topologically mixing models for discrete spectrum or for pure point spectrum. So like it's not. And curiously, like even though pure point spectrum is simple, like the topological dynamics of systems of these models, it's kind of like most results are quite recent. So more or less, I'll tell you. I'll show you the picture here. So we have pure point spectrum. And we have here topological rotations. But then we have another family here that is pure point spectrum with continuous eigenfunctions. So this pure point spectrum is we are still generating L2, but now we're asking that the functions that generate L2 can have a continuous representation. And this is something you see, for example, in substitutions. This result of Host that eigenfunctions, they have continuous representators. So this family is smaller. And there's a smaller family here that is called regular. I will say later what's regular, but maybe you already know like regular toplets or other regular Meyer sets. So actually, most of the typical examples you see of like quasicrystal behavior are regular, or like Robinson, or so many of them are regular, but there's different, like regular and pure point spectrum is like you can find very crazy examples here, where like for example, there's examples where the fibers of the maximal equicontinuous factor, they're all infinite. So there's so kind of like these pure point spectrum systems. They have like some diversity. It's not. Okay, so this is kind of like the classification. And one thing I'm interested is in these three properties, so regularity, pure point spectrum with eigenfunctions, and pure point spectrum. I want to understand them without looking at the spectral or the factors. Like I want to understand just with dynamics what they mean. And in general, so the question I have is kind of like, how can these properties be interpreted using predictability properties? And we'll see what I mean by this. Okay, so let's start with the rotations. So this result is kind of folklore, not very difficult. But maybe it's in Walter's book. Yeah, it's in Walter's. I think it's in Walter's book. Maybe it's also in the Helmholtz von Neumann. So a minimal system is a rotation, on a compact abelian group. If and only if it is equicontinuous. And this means that all the elements in the action are an equicontinuous family. So this means for every epsilon there exists delta, such that if 2 points are less than delta, then the action on the points is smaller than epsilon for all elements in the group. And why is this predictability? So this is more like this is starting to be like a. So rotation means that every element acts like a rotation. So you have a group, an element of the other group acting here acts like a rotation. And this is where like more topological dynamics start appearing, because like rotations, they are isometries. But isometries is not a property that is invariant on the topological conjugacy. So the property that is more like topological dynamics is equicontinuity. And equicontinuity has a flavor of predictability, because if you have some information about some point, you can predict how the orbit will be. If you make an experiment and you make a mistake of 0.001, if the system is equicontinuous, you will still be able to predict what happens. But for example, for subshifts, and also the lone dynamical systems, the Lone, we have for minimal. We have equicontinuity if and only if periodic. And periodic now, what does periodic means is with finite information, but sufficiently large, we predict all the behavior, all the orbits. Okay, so if you know the period and the sufficient finite information is the size of the period, then you can predict how the points will be. Okay, but now let's look at some regular systems. For example, let's look at so let's look some examples. So let's first look Sturmian. What happens if I give you finite information? And then let's say I have 0 and 1, and I give you some finite word, and that's all I'm telling you. So this, in a way, what you know in the coding is that you have some neighborhood here. And you want to look at how the other points in the neighborhood will behave. Well, most of the time you will be able to predict. The only problem is when this neighborhood is at the boundaries. At the boundaries you will have problems because then you will have like multiple. But this only doesn't happen that often. So this will be in the boundary, like the smaller the boundary, the less it will visit here. So for the Sturmian, if I give you finite information, I can predict the orbit with a very high density. And and also like another example where you can see this behavior is Robinson. Because you have kind of these squares, and then you have like some bigger squares, and then maybe some bigger squares, and the density of the squares of bigger sizes decreases exponentially. So if you are given finite information now, it means you have information on some square, and now, for example, if I see one of these squares, I can predict the squares, and but then I won't be able to predict the big squares. But the big squares only have some small proportion of the space, so the part where you cannot make prediction is small. Okay, so now I'll try to write this formally. So first, so now I'll just do things for subshifts. But the results are general. I mean, these are also for like RD or like or amenable groups. Like, but I'll do everything for subshifts. So from now on, just so for a set, a subset in set of the D, this is the upper density is you take A intersection So you see the proportion of A here divided by the size of the cube, and then you take the lim sub as n goes to infinity, and this is upper density. Yes. Thank you. Yes, 2n. 2. Actually, asymptotically it doesn't make. The D is important, yes. the D is important. Okay, now. Definition. Let X, I don't know, we can do it 0, 1 if you want, but it can be any alphabet. A subshift we say X is diameter mean equicontinuous if for every n there exists m such that for every pattern, so this is kind of the finite information, or this is like a word in higher dimension. So so this is a function that goes from so you can think it's like a restriction. There exists a set with high density and in this high density, we will have the same such that for every xy in the cylinder set of the pattern, so kind of like every, so the on this cube, x and y are equal to there is w. This implies that xi is equal to yi for every I in the set A. So if we have some sorry, this needs to be m. So if we have this finite information, so it's this kind of this square, we have a set where there cannot be, like all the points that share this initial information will be equal on this set, on this very big very big set. Because in the topological version, you need to use a diameter to define it, and it's similar to another property called mean equicontinuous, but you replace the mean, and the diameter is because in for topology you need some diameter. But here because I'm doing the symbolic, you don't see directly the diameter. I mean, what it means is like if in dynamics it means like if a set is small, then the average of the diameter will be small. Or if you have a ball and you see the orbit of the ball, and then you take the average of the diameter of the ball, it will be small. That's why it's diameter. And the theorem.
So what is that? The A is for all points in the set simultaneously?
Yes. Yeah. Yes. Yes. So. Yeah. If actually if it's not for all the if it's only for if the A depends on the XY, that will be the mean equicontinuous. That will be the pure point spectrum with continuous eigenfunctions. So it makes a difference. It actually is. So this is a result with Tobias Jäger and Xiandong Ye. A minimal system is mean equicontinuous if and only if it is regular. So I'll tell you what regular means is there exists. So this is the definition of regular group rotation CD acting on some group H and a factor map so this factor map is actually it's the maximal equicontinuous factor. And then we have the measure. This is kind of like the hard measure on H. And what we want to count is the points where the pre-image is just one point. So like these are the singleton fibers. So and this is the hard measure. So for example, in a group rotation, this is just in a circle, this is just Lebesgue measure, or this can be odometer. Usually this is like either a torus or a circle or odometer. So this is equal to 1, and this is kind of, this coincides with the regularity of like with the window on the major sets or on the toplets. So this is kind of like so this here in this definition we need to look at the maximal equicontinuous factor, and this definition here is more like a dynamics and it's kind of like predictability and this kind. Okay, I'll keep that one. Okay, so what happens now in the other? So there are examples that don't have this property and still fall in the kind of pure point spectrum, or kind of so there are example, toplets. There also, so this is kind of a minimal systems with a pure point spectrum and continuous eigenfunctions where every fiber is infinite. So every fiber of the maximal equicontinuous factor. So these are very strange, and this is built upon work of Glasner and Weiss by doing some proximal extensions, like generic proximal extensions. And I think this is kind of like this is also kind of similar to Anosov-Katok constructions. So there's these examples are kind of very strange, and they don't. The toplets are not that difficult to construct. These ones are more strange because this is a genericity argument. But so these ones are here. If you want to go here, you need like the topological mixing with pure point spectrum will be here, because then it will not have pure point spectrum with continuous eigenfunctions. So these are like topological mixing. So now I'll tell you how to characterize this. So I'll be I will be a bit informal. Definition. A subshift is a mean equicontinuous if for every n there exists m such that if the distance of 2 points is less than 1 over n, then there exists. But now this set depends on x and y. So this is the difference. Yes. 1 over n. Yes. Okay, so this is slightly different now, but it makes a big difference because these systems are always almost automorphic because you have singleton fibers, and these systems here they don't necessarily have to be almost automorphic. And we also in this paper we also have a characterization of when these systems are almost automorphic. And then here this theorem. This is Topnarovich, Glasner, but also Fuhrman, Brother, Lenz. A minimal system is mean if it continues, if and only if pure point spectrum with continuous eigenfunctions. And the last one, I'll be less vague, more vague. A system has pure point spectrum if and only if it's mu mean equicontinuous. And so here, this is for all x, y with this property. And what changes in the mu mean is we just ask for like a high probability. If you have a ball and you pick another point in the ball with high probability, you will be able to predict. So this is kind of prediction with high probability. So what we change is this for all becomes probabilistic in this definition. So this kind of so with these three results, we kind of have like the predictability versions of this. I mean, starting here with the equicontinuity and this the regular. So we have this okay, but so already people mentioned the Thue-Morse. So Thue-Morse is not okay. So questions. So what about Thue-Morse? So this so for me there's a difference between kind of quasicrystals, studying quasicrystals, and a periodic order. For me, a periodic order is any like structure or order you give to non-periodic systems. But quasicrystal has this history of the diffraction spectrum, and so you're expecting some properties. And the Thue-Morse doesn't have pure point spectrum, so Thue-Morse is not here. So there's another layer that can be studied here. That is Kakutani equivalence to rotation. So this, so instead of asking for an isomorphism to a rotation, you can ask for Kakutani equivalence to a rotation. This is weaker, these systems still have a zero entropy. These systems can be mixing in the measure sense. So but you have some kind of nice examples here, like you have all substitutions. You have horocycle flows. You have finite rank. So this is kind of like, for me, this is kind of like also lies in the aperiodic order. And and this sometimes is called loosely Kronecker, or some people call them loosely Bernoulli zero entropy. It's the same thing. This is very weird, but it's kind of cool. That kind of Bernoulli property is also similar to a Kronecker property. And we have so in work with the Dominic Fietniak, we have a predictability characterization. And here, there's kind of like in all this work, there's kind of like a Hamming metric hidden. And for the Kakutani equivalence, you need to forget Hamming metric, and you need to worry about the F-bar metric that is kind of studied in by Feldman and Katok. So it's actually a very natural characterization. It's very similar in flavor to this kind of definitions, but instead of comparing I and I, we allow that sometimes there's some shifting. So sometimes you compare points with nearby points and not necessarily to the points that are in the same position. So there's this, and there's also, and we also, with a student, we're also studying other predictability notions for two-emors, kind of like, so I will not, but I hope this, we can have it soon, but there's, so if you don't like the two-emors in the Kakutani equivalence, there are other ways to study two-emors. If you're interested, I can tell you the definition in the week. There's another result in a periodic order that I want to mention. Maybe it's relevant to. This is with Barbieri and something Lee. So let X be the support of a finite range Gibbs measure. So for example, this already contains all the SFTs, and this is also related to something called topological Markov property. This has been was introduced by Siamak and other people, and has been also studied by Nishant and Ronnie, and also Tom maybe will mention it. So it's kind of like a very natural property that appears when you take supports of Gibbs measures. And what we proved is that if X is minimal, then it has zero topological entropy. So any finite range potential. Mm-hmm. In any finite range potential, you take the support. If the system is minimal, it needs to have zero topological entropy. And so this is a generalization of quas and throw. So they prove that SFTs, minimal SFTs, have zero entropy for set the SFTs. So this is kind of this is more general because all the SFTs are contained here. But then you have examples that are not SFTs. That you have these supports may not be SFTs, but they always have this kind of this property here. So immediately, if you are like looking at this kind of ground stuff, and if it's minimal, at least you have zero entropy.
So they're probably concentration invariant?
Yes. Yes. And so, okay, so one question that I think is interesting is like generic. So pure point. So I mean, this is kind of connected to the result of Gonzalo Contreras, where like for set systems, for Holder potentials, generically you have a measure supported on a periodic point. So kind of like something like a crystal. So I think maybe maybe if you on higher dimension, what you get is kind of like something with pure point spectrum, or so I don't know. I think there's different ways to ask this question, and it's probably a hard question. Okay.
Maybe we could think maybe we could have periodic measures.
Yeah, maybe yes. Yeah, it's not. I don't think it's known that they are not periodic. Yeah. So okay, I think I want to finish.